Good. So, hi everyone. Thanks for joining. I'm over in Boston. It is snowing. God bless Seattle. So nice and warm compared to here. But today we're going to talk a little more about particle filters and think a little more about other ways of doing filtering, right? So, let's start by just recapping a little bit of what we started thinking about. So, some logistics are project two is already underway. You can start early. Um, you don't want to have to like tune things on the car in the last day. It's a pain, right? So the more you can start early, the better. The other thing is we're gonna have our first seeded paper discussion. I'll send out instructions for that early tomorrow morning, but it'll be on next Friday, right? And so you'll have around a week to do it, and it should be it's relatively low pressure. Okay, so any other questions, things that anyone wants to discuss? Looks like no. It since I can't see you guys, you have to speak up if anyone has to say anything. So just please unmute and speak up. Um, Good. All right. So let's start with the recap, right? So we said let's change our way of thinking about filtering. We were thinking about cubes with lots of empty space. We said, okay, we're going to go from cubes with lots of empty space to a different representation of particles. So we said let's represent things as a list of particles where you have, likelihood where there's where or you put particles where there's likelihood and you represent likelihood by duplicates, right? And so if you had a lot of S40, you would have duplicates. If you had a little bit of S2, you'd only have one, right? And so you're trying to change this to be a list-based representation, which is a list of particles, right? And so that was our basic premise. And the nice part is that you're not scaling poorly with dimension in the way that you're not wasting all of your memory and computation on empty space, right? So you're being a bit more memory and compute efficient. And so if we think about this from the perspective of Bayesian filtering, right, this is our representation of belief. And if you think about this from the perspective of Bayesian filtering, we're now going to go from this representation of belief to, the updates that we care about. And so we want to go from our previous belief, belief xt minus one, to belief bar, right? And belief bar, if you remember, um, was this combination, right? Belief bar was a combination of the previous belief and the dynamics model. And then we want to go from belief bar to belief, right? So that's going to be weighting things by measurement and then normalizing, right? And so what we kind of covered last time, and we'll recap a little bit here, is how do we instantiate this in the context of belief being represented as a set of particles, right? So you have a list of particles, and it's going to be like S1 to Sk. Now, belief bar will also be a list of particles. And so the first thing we want to figure out is what is the set of particles, S1 to Sk for belief bar? And then how do we update that to get a set of particles for belief, right, with the measurement model? And so the two questions we wanted to ask was how do we update the dynamics and how do we update with dynamics and how do we update with measurement, right? And so we're going to use a belief-based representation and just try to answer those two questions. Okay, so we talked about two different updates, the dynamics update and the measurement correction. And the questions we're going to answer are like, how do we sample from the product of two distributions? And how do we compute conditioning and normalization things with particles, right? And so when we have particles, it's maybe not as easy as when we had just, a table. And so our updates are going to look a little different. Okay, so how are we going to do this? Let's think about our dynamics update. And our dynamics update is basically saying we want to go from the previous belief with dynamics to the next belief, belief bar, right? And so all you're going to do is you're just going to sample forward using the dynamics model. So you're going to take your previous samples, run them forward through your dynamics model, and just sample a next particle, right? So for every particle, you're going to stick it into your dynamics model along with the action that you actually took. And you're just going to sample the next time step, and that's going to be your next particle, right? And so the way to transform your previous particles is you have a list. You're going to stick your list in one by one independently into your motion model, sample the next time step independently along with using the action that you actually took. And that new list is going to be your updated belief, right? And so really what you're trying to do is go from this list to a new list by just pushing things forward through the motion model. Okay, so the nice part about it is you don't need any Gaussian requirement. You don't need any linear requirement. You don't need any, you know, closed form solution. You just need to you need to be able to have a model that you can actually go forward through. You don't need to go backwards with the model, right? You don't need to um, necessarily compute gradients or anything through that model. Does this make sense? Um, okay. Um, Questions? Confusion? Was this pretty clear from the last time we did things? Okay, good. So that's our dynamics update, and that's great. The second thing we talked about was our measurement update, right? So our measurement update is a little trickier, right? So in our dynamics update, we just moved the particles, right? We had a list of particles. We moved the location of each of the particles. So if you look at our thing, right, we had these particles. We moved them to a new location, but you didn't like. There's no concept of a measurement there, right? And now we're trying to deal with this measurement. So we're trying to say like, well, we want to like weight particles by how likely they are. But we don't really know how to like change the list of particles, right? So if you just had a list of particles, S1 to Sk, and you're saying, okay, I want to move the particles around based on like the measurement, it wasn't super clear how to actually move the particles around because this doesn't give us a way to sample new particles, right? This model just says what is the likelihood of a measurement. It doesn't give us a way to sample new particles. And so what we decided to do then was say rather than thinking of beliefs as just unweighted sets of particles, you're going to think of beliefs as weighted sets of particles, right? So you're going to have um, S1 to Sk, right? And you're also going to have W1 to Wk, right? And so you'll have S1 to Sk, W1 to Wk. And the point here is that instead of trying to change where the particles are, which is trying to change one of the S's, right? You're instead going to try and change the weights on the particles, right? And so initially we had all the weights as one, and now we're going to say, hey, you're going to take your measurement model, compute a weight, which is the likelihood of the measurement for that particle, divided by the sum of the likelihood of that measurement across all the particles, right? So let's say you had three different particles, you got, or four different particles, you got some measurement, you compute this guy's likelihood, and then divided by the sum of all of them, right? So it tells you proportionally how likely was it that the measurement came from this particular state, right? And that's going to be your weight. So if you look at this thing, your weights sum up to one, right? And so essentially, you can kind of think of your measurement update as reweighting the particles, right? So you're going to multiply by P of z given x and normalize, but you're going to get these reweighted particles. So some things that were maybe less likely to produce a measurement will become large or will become small, and things that were more likely to produce a measurement will become large, right? And so you're able to incorporate the measurement into your particles by adding in a weight. Make sense? Everyone kind of with me? Okay, I'm gonna assume that silence means yes. And so um let's keep going, right? So this is our two updates, measurement and dynamics. So that's the first thing we talked about, right? We're not, since I'm not in person, I can't be a hypocrite and ask you guys for participation. So everyone gets participation today. It's great. Um so let's keep going with resampling, right? So we talked a little bit about resampling earlier. So we said that as we go across multiple different time steps, right? These things might not be numerically stable, right? So you're like doing this thing of moving the particles, then you're reweighting them, then you're moving them, then you're reweighting them, right? And so if you're multiplying these weights across every time step, some weights might get really large, some weights might be pretty small, right? And so, for instance, you're multiplying a bunch of these importance weights. You might have things blow up and get numerically unstable, and you might have particles that get stuck in unlikely regions, right? And so you're like trying to estimate this distribution, but your particles are wasted in this part of the space. Right? And they're like really low weight particles, but they're wasted in this part of the space. That's not really capturing the distribution you care about. And so um, the this like multiplied weighting of particles across different steps is kind of undesirable, right? And so we're trying to what we want to do with resampling is trying to figure out how to avoid this kind of like cumulative weight multiplication. Okay, so the idea behind resampling, if you remember, was we're going to start with a set of weighted samples, right? So things like a set of S1 to SK and W1 to WK, right? And then you're going to say, hey, let me convert this into a set of um, unweighted particles, right? So you want to say, let me say I had S1 to SK and W1 to WK, and then I'm going to convert it into a set of S1 to SK prime which are different particles, but you like don't want to have weights on them anymore, right? But you want to say that you're going to replace weights by essentially things that are like duplicates, right? And so you're essentially saying that like I want to get rid of the weights to deal with the numerical stability by replacing weights with duplicates, like shift the balance of which particles are in your set, right? And so resampling is trying to like essentially convert from a set of weighted samples to a different set of unweighted samples. Okay. So the idea is that you would typically do this n times. So let's say you had n particles, you can do this n times to get new particles, right? The nice part about resampling is that you can also change the number of particles. You have a distribution represented by some particles. You can choose to go up in particles, you can choose to go down in particles, right? You're just resampling every time, which means that you decide the number of particles that are at the next step. Right. So, can anyone think of a scenario where you might want to, go up or down in particles? Any thoughts? Any brave Zoomers? No? Sad. Um, well, okay. So an example could be that imagine that you had a scenario where your belief is really narrow, right? Like you're pretty sure where you are, and you like have really low uncertainty, right? You've like narrowed your distribution where you have lots and lots and lots of redundant particles, right? Presumably in a scenario like that, you might want to reduce the number of particles that you have. And so it saves you memory, saves you compute. Um, but not everywhere. And so there's like a rich line of work on like being adaptive with the number of particles that you have. Okay. So if we think about resampling, right, it looks like going through things with a roulette wheel, right? So you think of a roulette wheel where the length of each arc is proportional to the weight of that particle, right? And you're essentially trying to draw, a bunch of independent spins on this roulette wheel. So you're gonna like spin it independently, and you're just gonna see which of the particles it lands on and add it to your set, right? So you spun it three times. It landed in, let's say W3, W5, W2, and your set is going to be W3, W5, W2, right? And so the thought is that the more weight your particle has, the more of the circumference it occupies, which means it's a higher likelihood of being resampled, right? Another way of thinking about it is in terms of this line, right? You kind of divide this line by like cumulative weights, right? So you can say that like 0 to 1 over 8 is WT1, 1 over 8 to 6 over 8 is WT2, 6 over 8 to 1 is WT3, right? So you have three particles. And then when you want to resample, you're essentially going to use your random number generator to give you a number between 0 and 1, right? And then you're going to say, you're going to essentially draw, you're going to have an arrow. So if you look at 0.97, you're going to have an arrow here. If you look at 0.26, I think you're going to have an arrow here. And if you look at 0.72, I think you're going to still have an arrow here. Is my math right? I think my math is right, right? So your original set of particles, you had, these three particles, let's call them A, B, C, right? Your new set of particles is going to be B, B, C. Right? So you had a weighted set of particles A, B, C with the weights, 1 over 8, 5 over 8, 2 over 8, and then you resample. I see a question. Was thinking about this the other day, but could the chance that the resample being drastically different from the true distribution be harmful? It's a great question. Absolutely, absolutely. And so this is an issue called variance that often happens, right? You have just like high variance resampling. So we'll talk about a technique that makes this less likely. Um, but one of the problems is that if you have a finite number of samples, like say you get unlucky and all your particles concentrate somewhere, right? Then it can get worse and worse and worse. And so the fact that it's different from the true distribution can be catastrophically bad when you have the variance issue, because sampling is probabilistic, right? And so we'll cover this issue in a little bit of detail in a few slides. Great question. Okay. Um, okay, so this was our concept of resampling, right? And so what resampling would look like in a particle filter is essentially you have a bunch of samples, right? And then you're just going to resample them by spinning your roulette wheel a bunch of times, and you're going to get a new set of particles, right? And so your new set of particles is going to be located in one of the same positions as the other particles, but the numbers of them can be different. Right? So remember that what resampling is not going to do is not going to create a new particle position. Right? So like let's say our particles were at positions S1, S2, S3, right? What resampling is not going to do is it's not going to create, or let's say, and they had some weight W1, W2, W3. It's not going to create a new S4 that you haven't seen. What it's going to do is it's going to like duplicate S3, right? And so you're like, think of it as like your motion model moves particles, so it can create new positions. Your motion model moves this to a new thing. Your measurement update reweights things, and your resampling just redistributes things, right? So your resampling is never going to create a new particle in a new position. It's just going to redistribute, if that makes sense. Okay. Everyone kind of with me on resampling? Okay. I'm gonna assume that's a yes. And so the idea here is that you would resample particles from your weighted distribution to give you an unweighted set of particles, and then you would repeat this process, right? So you would repeat this process of essentially um, motion model, measurement update, resampling, motion model, measurement update, resampling. And that's kind of what you're going to do in lecture two, in the project too. Okay, so let's kind of look at an example here, right? So an example could be, you had, if you remember my first example, um, you did your motion model, right? You moved from this step to this step. Then you conducted your measurement model. Your measurement model gave you a bunch of weights, right? What could happen now in our resampling update is you're going to construct this whatever line, right, with these divisions according to the probability under each of the weights. You're going to like resample, and now your resample distribution would be like doubled at one of the states, right? And so this is just a graphical depiction of what we said earlier. But what you'll notice is that earlier we had three states with different weights. Now you just have two states with one of them being doubled, and it's back to being unweighted. Right? So you no longer have this like repeated multiplication of weights. Okay. So an example of this is from actually one of Dieter's old experiments. They were trying to do museum navigation, right? So they were trying to navigate around this museum, and this is like a top-down floor map of where the agent thinks that the robot is, right? And so the initially you think your belief is the red dots, right? Your belief is really wide. It's all over. But then you cast your LiDAR. Your belief is more narrow, but it's not unique, right? So this pattern of LiDAR things that you got is not necessarily unique. And it's the LiDAR is noisy, right? And so as we said, we can't just collapse the belief. So in one step, you don't collapse the belief, but then you see that you like move the belief after one motion step. You take another measurement, it becomes more narrow. Then you move the belief with one motion step, you take another measurement, becomes more narrow, and you kind of like eventually converge to like a really narrow distribution, right? So this is something that they actually ran in a museum, and the cool thing was that they ran this around crowded people and lots of different obstacles and scaled it to a real system. So that was amazing. Um, Okay, so the overall particle filtering algorithm, the second version, right? The first version was motion model, measurement update, motion model, measurement update, keep multiplying the weights, right? Our second version is going to be start from your prior set of particles, move things forward through your motion model or your dynamics model, weight things by your measurement model, but then resample to get an unweighted set, then go back to moving things with your motion model and repeat, right? And so you can go through this process of move things, weight, resample, repeat. And that's kind of what your particle filter is going to do in version 2. Okay, let me pause here for any questions. Anything that was not clear here or feels like, yeah, anything we should talk about some more. Okay. Good. All right, so let's keep going. So now this is version 2. Clearly, there's a section 3, so there'll be a version 3. Um, but here's a simple thought experiment, right? Which is imagine that you had an equal number of particles, but you had a pretty small finite set of particles, right? And they're equally distributed. And all you're doing is you're just and you're just like resampling from a uniform distribution, right? What you'll see is when you like it's kind of like flipping coins and then sorting them into heads and tails, right? And if you flipped six different coins, um, right, independently, which is what you often do, the chance of it being 50-50 again with only six coins is not that high. It's like 30%. Right? So what'll happen is that as you keep flipping these coins over and over and over, like you can kind of think of it as like um, when you flip, because you have a small number of things in the limit of infinite coins and infinite flips, right? Then you like converge to 50-50. But when you have a finite number of coins, what'll happen is that the likelihood that you get unlucky and you just kind of like end up at a scenario which is like heads, heads, tails, 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 or something like that is non-trivial, right? And so what you'll see is that even if you didn't move the system at all, right, and you just kept resampling, you'll see that often the particles will all migrate to one room, which seems kind of like the wrong outcome, right? Um, if you're in a system like this, really, you shouldn't have anything changing. There's no motion, there's no observation change. The weights are all equal. Like, why is my distribution changing? Right? It's it seems like a suboptimal behavior for a system. And um, so basically, this kind of can be boiled down to the issue of variance. And when I say variance, I mean that like all of these like estimators, probabilistic estimators, only converge to the optimum in the limit of infinite samples, right? And so you have finite samples, there's going to be variance in like what outcome you see, right? And so if you have just a small number of things and you're like resampling a lot, the chance of this like pathologically bad outcome happening is high. And so there's a few solutions we can kind of take, right? So the first is just be judicious when you resample, right? So don't resample too much. So like for instance, if the robot is stopped, and you're not really getting new information, like don't resample. And so if you don't want to deal with like this variance problem, don't keep resampling or be like, a little more, how do you say, discriminative when you sample, right? So um, don't just sample willy-nilly, right? Like sample only if the weights have pretty high variance. So if the weights have really low variance, you probably don't want to resample. Right. So, for instance, if all your weights are equal, your weights have high entropy, the max and min weights are pretty low, then you might be in a scenario that looks kind of like this, right? Somewhat equal distributions. And if you're resampling, then you're like risking this like particle migration problem. And so, one thing you'll see in your homework is that if you resample too much, like take the same distribution, resample, just, do it for fun, you'll see that the distribution often just collapses. And so you want to be a little careful not to collapse your distribution this way. Okay. The second solution here is something called low variance resampling. And so low variance resampling is a slightly different idea. But low variance resampling, you can kind of think of it as like earlier what we were doing is that we were like sampling things independently. So I'd, um, sample a random number between 0 and 1, see where it lands, sample a random number between 0 and 1 independently and see where it lands, right? But what you can do is you can just sample one random number and then pick the rest of the particles equally spaced out, right? And so imagine you wanted to pick m particles. You can pick the rest of the particles equally spaced out. So you can say, my starting point is randomized, but if I want to pick m particles, my starting point will be randomized. And like every other thing that I pick is going to be a fixed distance away, right? Whereas in the previous case, what we're doing is we're sampling every time independent. And here we're saying these are not independent, right? You're sampling them together. But what that gives you is, but it kind of passes a sanity check, right? Because um, the number of these like equally spaced things that will fall into, a particular bin will still be proportional to how big the bin is, right? It's like if the bin is tiny, there's a high chance that you just skip over it. If the bin is not tiny, then there's high chance that you'll have multiple of these like equally spaced out things that fall in there, right? And so the idea here is that you like try to cover the space more systematically by just randomizing what your start point is, right? And then sampling like m equally spaced particles from there, right? When I say equally spaced, it's like you like have this line, you like drew these arrows to figure out where things were. You choose your starting point, and then you like choose the next set of samples by equally spacing things out. Um, and it's still you still have to choose your starting point randomly, um, but you can avoid a lot of the variance issues, right? And so, one way to think about it is that if you have this equally spaced particle thing, right? It passes our sanity check for like this equal number of rooms situation because imagine you had um, let's take a scenario where you had like six equally spaced things, right? Those are like your six particles. If you like considered this like equally spaced sampling scheme, right? It's not going to like it's because they are forcing the particles to be equally spaced in probability space. You're not going to like collapse them all to one room, right? They'll have like different outcomes. And so, um, yeah, I think this is an algorithm called stochastic universal sampling, SUS. And it's like common in genetic algorithms and genetic genetic evolution methods to reduce variance. And so it's a low variance resampling method, right? And so you don't lose you lose less particle diversity. You can show that it's a lower variance estimator for these samples. And so that's the one you're going to implement in your homework. So when you want to think about how to implement it, just think about picking an initial point and then picking the next set of points as just being equally spaced out with the gap being one over the number of particles that you want. Right? That's it. Okay. There's a few other practical concerns that come up with particle filters. One of them is saying how many particles is enough, right? Should we sample 10,000 particles? When should we reduce particles? When should we increase particles? And intuition here is that you typically need more particles at the beginning. So if you go back to our example here, you needed lots of particles in the beginning because you want to cover all the possible places it could be. But you see that it pretty quickly converges to something pretty small. So you probably don't need that many particles to represent a distribution like this, right? So you can like reduce the number of particles. And so there's a really, really nice algorithm by Dieter Fox and some others called KLD sampling. I'd recommend reading it. I might assign it as one of the recommended readings. I really love this algorithm. It's great. But it like uses the KL divergence to um, choose the number of particles, um, and essentially says that when intuitively it says when the uncertainty is low, you reduce the number of particles and vice versa. So that was pretty neat. You also have issues with overconfident sensor models, right? So if you have sensor models that are overconfident, you like assign kind of you like end up double counting things. So you like over index on your sensor measurements. And so there's ways to deal with this by like artificially squashing your sensor model probability. So you like raise it to a power of 1 over m. You can sample from a better proposal distribution. Um, and these can kind of help fix your problem. And you also have an issue of particle starvation, which means that there's no particles that are near the current state, right? So you might have like, for instance, like if you go back to our example in the museum, right? Like you might have like collapsed the belief to a point where there's like no particles around here, let's say, right? And then there's like this is never going to get weighted up and it may never get motion modeled into, right? So you're like you have nothing to weight up, right? So if you remember how we did things, we like moved particles with the motion model. We reweighted particles with the measurement and then we resampled to one of the existing positions, right? But what can happen is that let's say you really collapse your likelihoods. You had no particles over here. The motion model from here is unlikely to magically transport over here. And if your motion model is the only thing that is creating new particles, like how will I ever represent a belief over here? So you might have like starvation of particles here, right? So your particles ran away from here, and now like these particles are gone, and now you're in trouble, right? And so remember, you're only moving particles with the motion model, you're reweighting particles with the measurement model, and then you're like resampling them afterwards. But if you lose particles in some place, it can be hard to regain the belief. And so what you can often do there is you can kind of deal with particle starvation by just throwing in some new particles, right? So you can kind of like say that I'm just going to like once in a while seed a bunch of random particles to kind of maintain belief over all the place that I might want. So you might want to try that out in your here's an interesting experiment that you guys should run in your homework if you're interested, which is it's called the kidnapped robot problem. And so this happens in your Roomba too. So if you pick up your Roomba and put it somewhere else, it's gonna freak out because it's usually running a filter. And if you have these filters, someone picking up the robot and moving it into random space is not usually represented, right? It's not in the motion model we talked about. The motion model we talked about was like you were here, you'd go here, you'd add some noise. There's no accounting for the fact that someone has kidnapped your robot, right? And so in those cases, you might have particle starvation because hey, your like particles were not even in this area that you're actually at, right? So I would try seeing what happens if you take your car, pick it up, put it somewhere else, and see that the particles get starved. And it's a very easy thing to see in practice. So give it a try. Okay, so I think we have all the pieces we need to actually do project two now. We talked about the kinematic motion model for the car, right? If you remember, um, there's like a change in theta, a change in x, a change in y. We just got it from geometry and a little bit of integration. Then we talked about a single beam sensor model. So if you shot a LiDAR beam, we talked about four sources of error. We talked about some noise, uncertain objects, sensor failure, just random measurements. And then we talked about, okay, we have these motion models and sensor models. We need to do filtering. We can do it with a particle filter algorithm, right? So the particle filter does move particles with the motion model, reweight them with the measurement model, and then resample them, right? And then there's like tricks you can implement on top of it, right? That you just talked about. Any questions? Do we feel pretty confident for to like do the homework? Yes, thumbs up, maybe. Say one thumbs up. Good. A couple thumbs ups. Great. A heart. Nice. Great. Exciting. Thank you. So let's go from here to um, the last part of what I wanted to talk about today, which is Kalman filters. And so Kalman filters are not going to be on your homework. They're honestly a little complicated, but I think they're really cool, and I'm going to try and convey some intuition. Um, if you want to, I am gonna skip a little bit of math just for the sake of tractability. So if you want to like really get into the weeds, just come by office hours and we'll talk about it. Right? Um, but the idea of Kalman filters is, we talked about the dynamics update and the measurement update. So we're going from belief at the previous step to belief bar. We're going from belief bar to belief, right? And we had one way of doing it with a particle filter, right? Which approximated this with the pushing forward distribution. You just push it forward through a function. You approximated this with a reweighting operation and stuff around that, right? But it is an approximation, right? And so um, the the problem that Kalman and lots of others were trying to solve, I think this is actually largely in the context of the army when they're trying to localize helicopters and these kinds of things, um, was was this problem of can we get closed form computable updates? Can we get like a tractable update for Bayesian filtering, which is not approximate, right? But you can actually compute these integrals and these normalizing factors and so on for, right? So how do we get a tractable computation of a Bayesian posterior? So if you remember, when I say Bayesian posterior, it's like P of xt given u 1 to t and z 1 to t, right? So that's kind of your posterior, and that is what you implement with these steps. How do you get a tractable update for these two things? Um, we can't do it in the general case. You can't do it for an arbitrary probability distribution. But what Kalman and lots of folks try to do is like, can we choose a simpler probability distribution where it's tractable, right? And so the way we're going to do this is let's talk a little bit about what system they chose, right? Um, and then we can kind of make it more complex. Okay, so their solution was to represent the dynamics and motion models, or the dynamics and observation models as linear Gaussian models, right? And when I say linear Gaussian models, I mean that your um, your likelihood was essentially a Gaussian model where the mean is like a linear function of xt minus 1 and ut and some variance. And your measurement model is again a Gaussian model where your mean is some linear function of xt and some variance for a Gaussian, right? So both of these distributions are essentially Gaussian, and their dependence on the dependent variables is linear. Right? And so what we're going to show is that in this case of linear Gaussian, you can actually do something tractable. Right? And so this is the basis of this whole field of linear control, linear state estimation. Um, and it's a really powerful method. So, so how many of you have remember how Gaussians work? Thumbs up, thumbs down. No, I got a no. Okay, some thumbs ups. Okay, so we'll do got a clapping. Nice. Um, and let's do a little bit of a recap, right? So remember a Gaussian, right? A univariate Gaussian is a probability, it's a continuous probability distribution with the mean mu and standard deviation sigma, right? And so you're saying x comes from mean from you say you represent it as n or whatever, math cal n of mu and standard deviation sigma or variance sigma squared, right? And the likelihood, right, is represented as 1 over square root 2 pi sigma exponential negative x minus mu the whole square by 2 sigma squared. Right? And so this kind of looks like, um, distribution that looks it's like a bell curve, right? And so you can think of the bell curve as being centered around mu, and the width, the variance determines the width of the bell curve, right? And so you can say that like 34% of the mass lies between the mean and one standard deviation, and then it kind of goes much lower from there. Right? And so um, that's like this is how you think of it in one dimension. You can kind of think of the mean as where the Gaussian is centered, and the variance is how wide it is, right? Um, and so when you're really uncertain, variance is super high. When you're really certain, variance is super low. Variance is always positive. Now, if you go from a 1D Gaussian into a 2D Gaussian, right, is when you go from, it's like from a scalar to a vector, right? So you often denote it as mu and capital sigma, right? And so when you think of your random variable, let's say it has two entries, xa and xb, your mean is going to be mu a, mu b, a vector of two. And your covariance matrix is going to be a four, it's going to be a two by two, a four entry matrix. It's going to have two by two. And it's going to denote the covariance between the different elements of your state, right? Um, and so I'll give you some geometric intuition, but first the like likelihood, it's very similar to what we had earlier, but it's just defined in matrix form. Um, so it's 1 over 2 pi d over 2. This is the determinant of sigma square root, right? And then times the exponent of negative x minus mu transpose sigma inverse x minus mu. So you can kind of think of this as the matrix form of the quadratic, right? So when you have the quadratic, you'd had x minus mu, the whole squared, divided by 2 sigma squared, right? This is just the matrix form of that, right? And so this is just the matrix form of the Gaussian earlier. But you can kind of think of it as like kind of like an ellipse. It's an ellipse where the center is determined by mu and sigma, and then the like orientation and the width of the ellipse is denoted by the covariance matrix, right? And so the often easy version of this is when the cross diagonal entries are zero. The cross diagonal entries are zero means that it's an axis aligned ellipse. So the ellipse will look something like this, right? And then the size, the like magnitude of these cross covariance terms tells you how like skinny or fat the like or whatever, like wider or short the ellipse is, right? Um, and so some examples here, you often represent them like this. So think of this as um, there's an X and a Y space, which is in the bottom, and then the height is denoting the probability, right? And so you can see that like on the left, you have um, a simple 2D Gaussian is the unit Gaussian, right? It's the unit Gaussian, which means that the mean is zero, the zero, zero, and the variance is like 1, 0, 0, 1, right? So you can see that it's axis aligned, right? So it's not, yeah, it's axis aligned, and it's equal dimensions on both, right? And then you can say that, okay, like I changed my like sigma and it made it like skinnier or wider, right? Along a certain dimension. And this is all still axis aligned. You can see that it's axis aligned, um, but it's like changing the width of the Gaussian, right? So you can kind of play around with Gaussians this way, but it's just kind of giving you some intuition for what a 2D Gaussian is. Okay, so now when you have these 2D Gaussians, there's some nice identities. And the reason they're nice identities is because Gaussians are exponentials, and exponentials under integrals have like nice properties, right? You can derive most of these with just completing the square. I can post some notes if people are interested. Yeah, someone who's interested, just comment on EdStem, ask, or I can send them out anyways. But basically, there's easy ways to derive this, but we're just going to assume they're identities for now, right? So basically, if I have X, which is sampled from a Gaussian with mean mu and covariance sigma, and if I have another random variable Y, which is AX plus B plus epsilon, right? So let's AX plus B, these are just like linear coefficients. Epsilon is noise sampled from a Gaussian with mean zero and variance Q. Okay. So Q is just a matrix for the variance. So you're saying that you have some Gaussian X. Then you have some linear function AX plus B plus epsilon, where epsilon is sampled from a Gaussian with center zero, variance Q, right? That is your forward propagation distribution or propagation function. Um, then if you work out the like formal math here, you can show that you can sample y from a Gaussian um, with mean a mu plus b and variance a sigma a transpose plus q. And let me kind of intuit this for you. It's saying that like, okay, you had a Gaussian that is your x, right? So this is a Gaussian, which is your x, mu and sigma. And now you like sent it through a linear function, which means that you can kind of think of it as the linear function moved the mean, right? And the way it moved the mean was just like literally sticking in the mean into the linear function. So you like move the mean to a mu plus b, right? And then you're trying to that's why it's a new it remains a Gaussian. Gaussians under linear operations remain Gaussians, right? And then you're saying like you move the Gaussian to a mu plus b, but the variance changed. So if you have a random variable, if you have a random variable x is equal to some, or maybe let's call it something else. Say if you have a random variable y is equal to ax, you can show that variance of y is equal to a squared variance of x, just by the definition of variance. And so what the variance here would kind of denote, right, is you can kind of think of it as like here you move the mean according to the linear function, but you like scale your variable by x, which means your variance is going to scale by you scale your variable by a, which means your variance is going to scale by a squared, right? So you can kind of think of this as an a squared term, and you added some more noise to your system, which means you're going to add in q, right? And so you can kind of think of this as like this was your original function or your original distribution. You pushed it forward through some linear operation plus some noise. And so your new distribution is also going to be Gaussian, but with the mean shifted linearly and the variance scaled and scaled quadratically, and you add the extra noise that you added in, right? I'll show some more geometric examples here, but let's just kind of think of this intuitively. It's like you have a linear function, y connected to x, and you just propagate things forward. And then you have conditioning, right? Which is saying that like this one's a little harder to intuit, but basically what it's saying is that if you had a Gaussian distribution, right, and you had like a dependent variable y which had a linear dependence, right? You're saying that like if I knew what y was, it also gives me information about x, right? And so it's basically saying that because x and y are not independent, this was your x, you got some information about y. This information about y can help narrow your distribution of x, right? And so you can see that what's going to happen here is that your mean is going to be shifted, and so, in some ways, your mean is going to be shifted depending on the difference between the y that you observed, y not, and you know, the y that you expected, which is c multiplied by the mean of the previous mean of x, right? And so you're going to look at the difference between them, and then you're going to kind of you're going to move your mean in that direction. And then you're going to try and shrink your variance. So this is kind of think of this as shrinking your variance, and think of this as like moving your mean in the direction of variance, in the direction of evidence, right? And so this one's a little harder to understand, and we'll go over more intuitive examples, but try to think of this as like shifting your Gaussian with a forward operation, and try to think of this one as if I had more information on a related variable. So you don't have information about x, you have information about a related variable y. It tells you how you adjust your belief about x, right? And so from here, you can kind of see where I'm trying to get at, right? If your if your things are linear and Gaussian, this kind of looks like your dynamics model, and this kind of looks like your measurement model. And we're going to kind of work those out next time. Okay. But yeah, let's kind of pause here, and we'll go over the details again on Monday. All right. Thank you all for attending. See you all on Monday. Unless there's more questions, I'm happy to stick around. Thank you, Devin. Do you have a question?